The gas law equations P1V1 over T1 equals P2V2 over T2 and PV equals Nrt are made up to work for ideal gases. Now, ideal gases really don't exist. They don't follow exactly the same rules as real gases do, and we make up certain assumptions that will be suited to real gases so that we can make use of these equations. And we just make the assumption that when we're working with a real gas, it's really an ideal gas, even though that's not truly the case. Well, let's look at some of the assumptions we make for ideal gases. The first one is that volume taken up by gas molecules is zero. Well, this isn't true, but it's near enough to being true, because we know that molecules are not very large, and they will be small. The volume will be small compared to the size of the container. Secondly, we assume that all collisions are perfectly elastic. Again, that's something we know that's not true, because what happens is a gas molecule will lose a little bit of energy when it collides with another gas molecule or with the wall of the container. As temperature increases, kinetic energy of the molecules increases. Well, this is true for both real and ideal gases. And that the molecules do not attract or repel each other. And we know for real gases that this is not true, but generally speaking there's a little bit of attraction between molecules, usually something electrostatic that's occurring. But for ideal gases we assume that this is not the case. And the other thing is that gases consist of extremely tiny particles, and that's kind of related to assumption 1 here about the volume taken up by the gas molecules being zero. So the consequences of this are that real gases will behave most like ideal gases under conditions of high temperature and low pressure. So let me show you a diagram of that. Under conditions of low pressure and high temperature, what we're talking about are gas molecules, a small number of gas molecules in a large container, and they're moving very, very quickly. And the more quickly they're moving, and the fewer there are and the lower the pressure, the more of it this real gas will react like an ideal gas. However, if we reverse the situation, we have a high pressure and a low temperature. That means we've got a lot of molecules in a very small space, and they're not moving very fast. So in this instance, they're going to act more like a liquid. So gases under those circumstances don't tend to act like gases at all. They'll tend to act more like liquids. A couple of other consequences of all of this is that small molecules will move faster than large molecules, and what we're talking about here is their molecular weights. The smaller their molecular weights, the faster they will move. So helium will move faster than methane because its molecular weight is lower. The average kinetic energy of the molecules will depend only on temperature. At absolute zero, all molecular motion ceases, and this is why all the temperatures that we use when we're talking about those gas equations will be converted to Kelvin, and it gives us a reference point. Standard temperature and pressure is defined as being 1 atmosphere and 273 Kelvin, or if you like 1 atmosphere and 0 degrees, or 760 millimeters of mercury and 0 degrees Celsius. And 1 millimeter of mercury is considered to be 1 torr. So all of those matter for standard temperature and pressure. And what also is very important is that 1 mole of any gas, doesn't matter what the gas is, will occupy 22.414 liters at standard temperature and pressure. So that's a very important law. It doesn't matter what the gas is, 1 mole will always take up that much volume. The next one is Boyle's law, is a consequence of all of this as well, and that is that P1V1 equals P2V2. Let me show you some examples of that. An example would be if you've got a diver, and this is supposed to be water here, and the diver is letting out little bubbles of oxygen, and what happens is that at high pressure, which is sort of deep in the water, the volume of the bubble will be small, but as the bubble creeps towards the surface, because its density is less than the density of the water, what's going to happen is that the volume of the bubble is going to increase, and that's because the pressure is decreasing as we get closer and closer to the surface of the water. So what we get from that is that pressure is inversely proportional to volume, and the way we express an inverse proportion is to say it's directly proportional to 1 over volume. The other way of expressing that is to say that P times V is going to equal a constant value, And if that's true, then we can say that P1V1 equals P2V2. So what we're saying there is that if we've got a bubble here that's got a small volume and a large pressure, then that's going to have the same value as a bubble that has a large volume at a small pressure. So that's why P1V1 equals P2V2. And that's going to be the basis of Boyle's law. We can also talk about Charles' law, and an example of this is, let's say you've got a tire on a car, and the car has been resting all night and then it's driven. What happens is that the tire will heat up, and as it heats up, what's going to happen is the tire is going to expand. What we get from that is that volume is directly proportional to temperature. So as volume goes up, temperature goes up, and vice versa. The other way of expressing that is that V over T equals K, and V1 over T1 equals V2 over T2. And these expressions will all reflect the fact that as volume goes up, temperature goes up, and as temperature goes up, volume goes up. And as volume goes down, temperature goes down, and vice versa. Right, so you can see now the relationship between pressure and volume and temperature. Now, as those are combined, they give what's called the combined gas law, which is P1V1 over T1 equals P2V2 over T2. And this will only happen when there's a change in conditions and a constant value for the moles of gas. The other important equation we'll be using is PV equals Nrt, which is also a consequence of the combined gas law as well. And we're going to use a constant value here for R, 0.08206 litres atmospheres per mole per Kelvin, and we can use this equation when we need one of these and we have the other values, and you'll see examples of those later on.